So we will start this afternoon session of this PyData Madrid, and we will have Tomás Gómez Álvarez-Arenas that will talk about the inverse problem. So an applause to Tomás.
Okay, thank you very much for the introduction. So, it's a little bit different topic now. I think it's good for siesta time. So, well, my name is Tomás Gómez, as you said before. I'm working for the Spanish National Research Council here in Madrid at the Institute of Physical and Information Technologies, not far from here. So. And the main topic of the talk is the use of Python implemented gradient descent techniques to solve inverse problems. So, is that working? Okay. So first, a brief outline of my presentation, just a definition of what the inverse problem is, in case you are not familiar with the concept, some application of the inverse problem, the description of what are the main elements of this problem, and then a brief introduction to optimization algorithms, and mainly focus on gradient descent algorithms, and finally a Python implementation of gradient descent algorithms for inverse problem and a few examples. So, okay. Just to put a framework of the work today, I would say that at least my work, and probably the work of most of you, is focused on data and on extracting knowledge from the data. And anytime we try to solve this problem, our main hypothesis or our starting point is the assumption that these data contain information, and moreover, that this information is useful. So whatever data set can be complex, can be simple, can be large, can be small, can contain a lot of variables, or maybe not a lot of them. But whatever the data set, we want to extract this information. So the information can be varied, very deep within the data set or not. But what we want to do is to extract this information and transform this information in knowledge. So there are a lot of techniques to deal with this problem. And depending on the kind of information we want to extract, depending on the application, and depending on the complexity of the problem, we can use regression techniques, machine learning, bayesian inference, statistical analysis, or it can be an inverse problem. This list can be much, much, much more longer, as you can imagine, but just to mention a few cases. So today I'm going to focus on the inverse problem. So I'll give you first a definition. It's going to be an extremely simple case to illustrate what I'm talking about. So don't worry about this. So to define the inverse problem, we have to first define the direct problem, because the inverse problem is going to be the opposite one, so the other way around. So direct problem, a very simple case. That one, nice. So imagine that we are on the top of Pisa Tower and you drop a ball. You know the model that describes how the ball is going to fall. And we know the parameters of the model. We have two parameters, the A and the gravity. And then we can calculate the position of the ball at any time. So I have the model, I have the parameters, and I can predict straightforward the results. OK, inverse problem. Same situation. I have the same model. I have the position of the ball at several times. But what I want to do now is to, assuming that the model is OK, and assuming that I have the measurements, I would like to be able to extract the model parameters. So I would like to, from this measurement, to be able to extract the original height of the ball, and the value of the gravity, right? And I will have a prediction, and I will try to fit the prediction into the position. And by fitting this, I will extract the parameters. So it's a very naive example. Let's go to something more, a little bit more serious, right? So one example, gravitational waves. Probably you have heard of that recently because there was a lot of interest in the media. And the point was that scientists observed something like this, and they presumed that this is the result of two huge masses orbiting each other, around each other, and eventually collapsing. And well, eventually they came up saying that they confirmed Einstein theory because they were able to fit the prediction of this model into the measurement that we have there. And by fitting this model into this prediction, into these measurements, they were able to say how big were the masses, how much time ago this happened, and what was the amount of energy released when both masses collide. Well, it's amazing, isn't it? Just from this, that you can predict the masses of two big black holes orbiting each other and eventually colliding. Well, by the way, this is from Python point of view, this is quite interesting because all calculations are made using Python, and there is a very nice tutorial. You have all the data, you have all the calculation there, so if you are interested, you can have a look there. Another example is an ichographic signal. So you have an ultrasonic signal going through a tissue, and then I can get a spectrum of the signal, something like this, and I can predict how will this spectrum look like depending on the properties of the material. But what about if I have this measurement there, and by solving the inverse problem, I will be able to, just from this measurement, to be able to say how many layers of tissue, what are the thicknesses, what are the densities, what are the elastic constant, what is the mechanical damping, and how is the change of the mechanical damping with frequency. Wow, amazing again. So it's from just a measurement, you are able to extract a lot of information from the medium or the material or whatever you are getting this information from. And you just have to assume a model, and you must be able to optimize, and this is the key point, optimize the fitting of the model with the measurements. Okay, so application, three main applications, and you probably already know about them. So the first one, maybe the more clear, is you can obtain the model parameters. So you can obtain what are the masses of these two big holes orbiting each other, or you can obtain the parameters of the tissue, or you can obtain whatever. But you also can confirm the model, because if the model is able to fit the measurements, well, it's quite reasonable to assume that the model is working okay. This is what scientists did before when they say that they have confirmed Einstein theory. But this is a third point. Yeah, I probably have some data, and I'm not sure what is the best model for this data. I can try to fit different models to a data set, and eventually I can come up with the model that best fit this data set, so I can make a model selection. Okay, what are the main elements of the inverse problem? So the main elements is you need some data, you need a model, so you must guess what are the physical model that justify this data. You need an error function. It's normally an L2 model norm, and just to compare the prediction with the data. And then you need an optimization algorithm. And the work for this optimization algorithm is going to find out the combination of model parameters that achieve the best agreement between the data and the model according to the error function. So the output are going to be the parameters of the model. Your model can be analytical, can be a computer-generated model. You can have 2, 3, 4, whatever many parameters, and the output of all of these things will be to obtain the model parameters. Okay, maybe most of you are more familiar with machine learning than with inverse problem, so just compare them, because they're really similar. So assume for a moment that I don't care very much about the model. So if I don't care very much about the model, I don't care very much about the model parameters, clear. And so I don't want to know what are the model parameters, but I want to be able to guess what will be the model output for a new data. This is machine learning. So not fun. So back to the inverse problem. A couple of additional elements. In many cases, it's going to be an iterative solution. We're going to need an initial guess. Okay, you have to know something. If not, it's going to. In many cases, you have an initial guess. If you are sure that there is only one solution, this can be a completely uninformed initial guess, or whatever, and the model and the algorithm eventually will find the solution. Can take ages, but it will convert. If the problem is more difficult, you need a good initial guess. And you probably need some constraints. Constraints as a relationship between the variables that you know that must be fixed. A very interesting property of inverse problem is, I don't know if you're familiar with this concept. If not, you should. Is wall pose versus ill pose problem. And it's quite straightforward to go in the direct problem solution from this point to this point. But when you arrive here and you want to go back, you may find that there's no solution back, or that there are many solutions, or that the stability is not guaranteed. So if you start here, you may find a solution there, but you start in a slightly different place, you may have a completely different solution. So in general, people working in this field up to maybe 10 years ago, they tried to avoid always ill-posed problems, because working in ill-posed problems means that you are not quite sane. But now people are starting to work with ill-posed problems because, well, we have some ways to deal with that, but it's going to be a little bit difficult to explain that now. Okay. Optimization algorithm. So the core of the inverse problem solution is to develop an algorithm that is able to optimize the fitting between the model and the data. And just to mention a few of them, with the unique purpose to show you that there are many, many different options, and that solving inverse problems doesn't mean that you use one particular technique, but you can use many different ones. So most of them were developed in the 60s, and there's some of them more recently, but there's a lot of different algorithms. So, and there is a lot of Python implemented algorithm for that as well. So you have some of them in SciPy or SharePy or PIQT or LMFit. So they are already developed, they are there, and you can use them. So just to focus on one of them, the one in SciPy. So in this case, you have a lot of different algorithms, and you can choose the one you want to use. So the main point is to be familiar with the different methods, what they can do, what they can't do, so that you are able to know exactly that you are using the proper algorithm for the proper problem. So I want to focus on gradient descent algorithm because for, I think, 2 reasons. The first one is that it's pretty easy to understand the gradient descent technique. It's really easy. Implement a basic code for gradient descent is quite straightforward, so it's very easy as well. So it's very easy to understand how the model, how the code works, how implement the code, and to have a first feeling of what inverse problem is and how can you solve it and so on. So, okay. There are some implementation of gradient descent techniques, algorithm for Python as well. And, well, gradient descent is used quite a lot in machine learning as well. So if you are familiar with machine learning, probably you are also familiar with this method. And, okay, the key elements for gradient descent techniques for inverse problem. On the left, we have the key elements I mentioned before, so the data set, the model, the error function. And now the optimization algorithm is going to be a gradient descent algorithm. And in this case, the key elements are the initial guess, I need an initial guess because it is going to be an iterative. The step size, so it's the size of the step I take every time I go in the algorithm, and the constraints I use. So I'll show you in detail in what we have now. I would like to explain you the gradient descent approach. So you have the data, you have the model, and the model depends on the independent variable, and you have some parameters. Let us suppose that you have 3 parameters in your model. So we can represent them in a 3D space. We can use 5, but the representation will be much more difficult, as you can imagine. So let us suppose that we have 3, and the solution is somewhere, we don't know, and we would like to reach that point. You have the data, we have the model, and we have a way to compare the data with the prediction is the error. And we want to find the point where this error is minimum, that point. So the only thing I have is an initial guess. And I want to be able to go from this initial guess to the final solution. So the idea is to look around the point that you are at this moment, select a space around you with a discretization step, and then check all points, or check some of the points around you, find out the one, or not the one, find out a better point, because the error is less, and then move in that direction. So you check all the points. Depending on the dimension, the volume to search is going to be different. So if we increase the dimension, the volume increases very much. And so we want to find one point to move, and we take a step in this direction. And there's 2 different techniques. A systematic approach. A systematic approach means that you search all points around you. You search them all. And then you find out what is the best, that is, what is the point where the error is the minimum one, and then you take a step in that direction. But the other approach is quite interesting. This is stochastic. Stochastic means that you start searching the volume around you at random. And once you get one point that provides a better error, you go in this direction. If you start searching the volume around you at random, and at the first point you have an error that is less than the one you had before, you go in that direction and forget the rest. So what are the main differences? Well, the computational cost. In the first case, it's going to be constant, 3 to the n, and n is the dimension of the problem. But in the second case, it's going to be variable, clearly, because you can, if you are lucky enough, you just take one step, search one point, and go in that direction. The incremental improve, so how much improve you in reducing the error at every step is going to be different. In the first case, it's going to be optimum. You are getting the best improvement in the errors you can, but in the other case, not. Avoid local minima. Well, systematic approach can be not very good at this point. And same solution. Do you reach the same solution every time you run the model? With the first case, yes. But with the second case, maybe not. So you may have a cloud of different points around your final guess. And this is very good. Maybe you think it's not, but it is. Because this is a way to measure the precision of your method. Because you have a huge dispersion of any time you run the model doesn't mean that this is not a good solution. So you find a point, either stochastic or systematic, and once you get the point, you take a step in that direction, and you start again. And this will be the summary of the whole thing. So you initially guess the volume around you, you find a point, and you go in that direction, and if the error is good enough, you can say the problem is solved. If it is not, you start again, and so on. So a Python implementation. So I have the code slides. Well, the code is a Python code, and this is also a Python notebook that I will upload in the conference. Well, there are two main functions. One is the one on the bottom is the one that check the error around your point, and the other one is the one that is calling this every time you take a step in this process. So they are quite simple functions. And we also implement this function here. It's quite interesting because this function here allows us to develop a model that is able to run for whatever number of parameters, and you don't have to determine the number of parameters beforehand. So the model can run for 2, for 3, for 10, and you don't have to say how many beforehand. And then we define a class object for the fitting object so that we can do different things with that. So some examples, because with samples, I think the situation can be more clear. Very, very simple samples. Probably as simple as the Pisa Tower problem at the beginning, okay? Linear regression. So I have this problem, I have the data, and I have the model, and I want to extract the model parameters, so slope and intercept. So this should work, right? It does. And you can run the stochastic or the systematic gradient descent approach. And what we have here is a plot in the space of the parameters. So we want to know, this is our initial guess, and this is the target value. And if you store at each step what are the changes of the parameters, you can see that you are going from the initial point, and you nicely arrive at the target value. And this is the stochastic, and this is the gradient descent. And quite interesting is that the path along the stochastic approach is longer, clearly, but it is faster as well, because you don't have to search the whole volume every time you want to take a step. It can be much faster, and this is especially important in large dimension problems. In a large dimension problem, searching the whole volume around a single point can take ages. So you can run the stochastic case 2 times, and you are going to have a different path. Clearly, you arrive at the same point, almost at the same point. Okay. This is the red one is our target value. The yellow one is the solution of the problem using the Psi-P linear regress. And we run the model, the stochastic gradient descent model, 200 times. And I obtain these 2 different sets of data. So something like that, we have multiple solutions. They're very close, so it really doesn't matter. But we can be aware that, okay, there can be a problem. And we are plotting, from these 200 times, we are plotting all solution whose error is less than the minimum solution plus a 5%. Okay, we can reduce this limit. We can. We get rid of that. And the systematic gradient descent was on the wrong place. You can run the Python code all times you want because the model is going to be always the same, but every time you run the model, the noise is different. And every time you run the model, you are going to have something different because if the noise is different, the result is going to be different. And this is another case, for example. Okay, something similar. This is another one. In this case, the Psi-P linear regress prediction is the worst one. And in this case, if you reduce if you increase the precision you want in the solution, you get nothing. So you keep these 2, but they are really close. So you can be aware that you have 2 solutions, but they are very close, so you really don't care very much. Well, another case, very simple. It will be something like this. So you can do the same. Now the path to the solution is going to be a 3-dimensional one. And as before, stochastic case is longer, but faster. Run different times, you have different paths. And while you can run these different times, and you have a cloud of plots. And there's a function to plot this, and okay. Okay, something more complex. Let's consider signals in the time domain, and we are going to jump this one because nothing. Okay. this is what we call a linear chirp. I don't know if you are familiar with a chirp. A chirp is, for example, is quite used in electronics, in ultrasonics. A chirp is, for example, the sound that a bat produces to localize the prey, normally a moth, a poor moth. So this is a signal whose frequency changes with time. So this is the law that predicts this kind of signal. This is going to be our model, and we have 3 parameters, and we want to do the same. So it will be something similar to what we have before, and we can run the model and have a good fitting. This is going to be a gain linear chirp, something similar as the one before, but the amplitude is increasing as the time goes by. And we have an initial guess close to the final solution, and this is what we have. Well, you can compare the fitting of the two and the path in the space in the parameters space. And you can see that in the first case there are 2 clear legs. So we start going down and then we go in depth. But in the second case, we are missing one part. And this is because of the attenuation at the beginning. Because at the beginning the signal is so low, we lose some precision there, and we are not able to fit this parameter. So in this case, it will be important to be aware that it's going to be able to fit this parameter. So better not putting this parameter on the model because it's going to be completely misleading. And this is something related to model selection. So doing this, we learned that the model in this case is too difficult, so too complex. So this will be a kind of an ill-posed problem because in this case, we really get no information about the parameter on this axis here because we learned again. Another problem with signals in the time domain that change this way is that the initial guess must be very close to the final solution. If not, you can be trapped in a local minimum. This is one. You have a very good fitting at the beginning, a very good fitting at the end, but not in the middle. And because of that, this is a minimum, and you are not able to get rid of that. So you are trapped there. So you can increase the step size, and you can solve the first problem, but not the second. And a pretty good idea in this case is to work in the frequency domain. So we stop working in the time domain, and we transform the data from the time domain to the frequency domain, and we operate in the frequency domain. For those of you familiar with that, this is a fast Fourier transform, FFT, so the idea is to transform things in time. So this is the signal from this is what is called the mass chirp. Chirp is because it's a way similar to the one we have seen before, a mass chirp because this is the wave produced by these 2 big holes colliding and so on. And in this case, the law of the mass chirp is bottom right, and the measurements were on top, and the idea was to try to fit the model to this data. And the only thing authors in this paper said about this problem is just these 2 lines in a figure caption. And this is something very common in physics, engineering, biology, and so on and so on. All people trying to fit a model to some data, to extract some parameters, they normally say, we have done the fitting, and we have found the best fitting, and is this. And they normally do not say the details. And many, many, many cases, they only have an initial guess. They didn't have the effort, they didn't put the effort to try to solve the whole problem. So in this case, the original measurement was once the one top left. And for me, probably for you as well, this is pure noise. This is no more than noise. They translate to the frequency domain, they filter the signal, they get that one, and they eventually get that one. So another case, this is an ultrasonic signal that goes through a tissue, ecography, medicine, this kind of application. And this is the signal we have. We know this signal will present problems in the frequency domain, in the time domain, so go to the frequency domain. And this is what the signal looks like in the frequency domain. So you have a pattern of resonances, and you can try to fit. Well, the difficult point in this case is we have 5 parameters, quite a lot. And a very interesting solution is if, in many cases, to solve a problem means not only that you know about the algorithms, but that you also know about the specific properties of the problem you want to solve. And if you don't know very much about the problem, then you will spend most of the time in the algorithm learning about the problem. So in this case, what happens is that the last parameter is the one that determines this decrease. And this is the only one parameter doing that. So the idea is to forget this one, fit the first part of the curve, and now we have a 4 parameters problem, much easier to solve. And then use this information to go back to the previous one. And this will be the fitting in the first case, and then you have the other one. So this will be the similar images as before. In this case, you have to select what are the parameters you want to represent, because you only can represent 3, and you have 5, okay? Okay. A very interesting way to deal with a large dimension problem is this capability to split the problem into 2. So if I know that some of the parameters affect some part of my problem and some other affect other part, then what I can do is I can separate. I will reduce the dimension of the problem, and they can start fitting one part of the problem, then perform an early stop, go back to the others, and so on, until we arrive to the final solution. And very briefly, this is what we have done here. In this case, you have 10 parameters, and this is a very complex problem, but which you can start solving the first part, and then you obtain the first 5 parameters. You can use these parameters to have a rather good initial guess for the rest of the problem, put these on the problem, and try to solve the whole problem. So eventually we manage, but the main message here is that no matter the complex the problem is, there are techniques that enable you to extract parameters from simple measurement, and this can give you information about the medium you were investigating or the problem you were dealing with, that this can be completely impossible to imagine beforehand. So can arrive to the Q&A part, and just it's a kind of a joke. This is the direct approach to the Q&A question will be that you ask and I respond. The inverse problem is that I respond and you have to guess the question, what the question was. And this is clear that it can be an ill-posed problem, because if my answer is no, you cannot guess the question. But if my answer is yes, we have tried, well, you're sort of much closer to that, okay? So, thank you.
Let's thank Tomás. So we have around 5 minutes for questions. Questions? This interesting talk.
It was also to continue in the light-hearted tone that at last you see that these stochastic or exploratory ways need some hand-tuning on the number of variables that have to be sorted. One could even tell that you are conjugating by hand the stochastic gradient that you have to choose. But do you have some previous knowledge of which variables, or did you exhaust or was by chance?
Okay.
I'd like to extend a little the question. How much what you do by kind of optimizing that is intuition?
Yeah, I think it will be interesting to explore this idea when you have no information about the data. So this will be really very interesting. So, because you know that this can work when you have some knowledge about the problem, and you can do some kind of interaction with that. But probably it can be very interesting to try to do this when you know nothing. So try to guess different ways to aggregate your parameters and try to run the algorithm and to see what it can be very interesting, right?
Any other question? So let's thank Tomás. Oh, sorry, one more?
Thank you for the presentation. One question, when you use the stochastic criteria for the chains, how do you evaluate the convergence to the point?
Well, you have two different possibilities, right? If you, well, you can run the model with a problem that you already know, so you can check if what you get is what you're expecting to get. When you are using a problem that you really don't know the solution, you really don't know if your convergence is okay or not. One good way is to look at if you are having if you have multiple solutions or not. This can be a good approach to know how good is the algorithm performing. So if you have different solutions and you have no way to use constraints to eliminate some of this solution, then you may have a problem. But
we may have time for another question. No? Let's thank the speaker again.
yeah.